that last time. Pretty exciting stuff. All right, so I only have about 40 slides to get through today, so it should go pretty quickly. We're going to talk about the birth of the Earth today, hopefully. On. Okay. Oh, I guess this thing has to go into the computer. Somebody.
Let me take care of that for you.
Thank you.
Yeah.
So we've talked about the Big Bang. We spent 2 or 3 lectures talking about the Big Bang and how a tiny nugget of potential energy converted that potential into matter, protons and neutrons. And for about half an hour, as the Big Bang got itself started, for about half an hour, some of the protons and neutrons that were generated combined to form helium. So the universe started with helium and hydrogen. And we're talking about how the scientific story, the story that science can tell, contrasts with a lot of traditional stories. For ages, people have been asking, where did we come from? How did we get here? How did the Earth come to be? What are the stars? How did the stars get there? Are they eternal? Is the universe eternal? All of these questions have been swirling in the minds of humanity since time immemorial. We can be certain that our ancestors all had these same questions, and we live in a generation, one of the few recent generations, that began to put real, plausible, reality-based answers to these, and that's through the benefit of science. So we talked about the hydrogen and helium from the Big Bang, how it came together to make stars and galaxies. So in this picture, every dot you see is another galaxy with something like 100 billion stars and enough gas and dust to make more stars as time progresses. And then finally last week we wrapped up talking about the way that stars are alchemical forges. The elements that we see around us, the elements that make you and I, the carbon and nitrogen and sulfur and iron and so on, all of those elements were forged in the hearts of stars subsequent to those stars initially forming as just balls of hydrogen and helium. So we talked about how stars are alchemical factories in the sky, and they have the larger stars more massive than the sun, have a kind of onion-like series of layers. Interestingly enough, the smallest, lightest stars in the universe churn all of those layers. There are convective cells throughout the small stars that reach all the way into the cores. So smaller stars do a better job of burning their available hydrogen than do large stars. Large stars don't have as prominent and deep-reaching convective cells, so these larger stars tend to get this more definitive layered structure. And then we talked about how stars sometimes explode, especially the big ones. They get too big for themselves, and in a cataclysmic explosion that can outshine billions of stars otherwise existing in a galaxy, a supernova can, for a few brief days, outshine all of the stars in a galaxy as it emits a huge amount of energy, and all of those layers, those onion-like layers of heavier materials are ejected, or many of them are ejected into space. And it's such an energetic process that even some of those elements that started off as being just iron and sulfur and whatnot, they get irradiated with, bombarded with alpha particles, which are helium nuclei and other neutrons and protons and neutrinos and gamma rays. So much energy is available from the explosion itself in a few weeks that the heavier elements, many of the heavier elements that we see in the universe, heavier than iron, are forged in supernovas in a matter of moments. So, We talked about population 1, 2, and 3 stars. The current generation of stars, those of you who are here, is population 1. The stars that preceded it are population 2, and the oldest stars in the universe are population 3. Those oldest stars in the universe are ones that generated this sort of onion-like structure. Not that the new ones do too, but these first stars took hydrogen and helium, and from those raw materials generated carbon and nitrogen and silicon and other elements, and subsequently exploded. So a lot of the gas and dust clouds that astronomers have observed and measured in space, they can't go out and take a sample of them directly, but using spectroscopic methods to look at the light reflected off of the dust or emitted by the energetic heated up gas, they can tell what kind of chemical composition is there. And they've verified that indeed the big regions of gas and dust in our galaxy and in other galaxies is comprised of hydrogen and helium. Again, it's still the most prominent elements in the universe, but it also has a sort of a salting of these other heavier elements. And the detritus from these exploded stars, generations of exploded stars, hundreds and thousands and millions of these exploded stars, all of the stars from population 3 are gone. They were big, bright, heavy, short-lived, and explosive. And so they seeded the cosmos with all these heavy elements that waft around as these gas and dust clouds. And this is an image of the constellation Orion. And if you zoom into the constellation Orion, or if you zoom out from the constellation Orion, you still see these giant clouds of gas and dust. And within some of these parcels of material, there are wheeling, nascent, brand new stars being birthed. So you see baby stars coming into existence that are accumulating from the detritus of prior generations. The new stars are being born in places like this. And we know all of that from our position here on spaceship Earth, right? We can look out, and from a fixed point in the cosmos, relatively speaking, the fixed point of Earth, even though we're moving around the galaxy and all of that. But, you know, generally speaking, from our steady perch here on Earth, we can look out at the sky, and just by interpreting the light, and now, recently, the gravity wave radiation, and plausibly some of the neutrino radiation, each of these is a different signal that we can use to gather information about the wider cosmos. And sometimes a supernova is so energetic that it'll produce all three, neutrino radiation and gravity radiation and light radiation across the spectrum. And this is called multi-messenger astronomy. And this is a new thing that during the 21st century. Gravity wave astronomy, I think, is going to be one of the great tools to better inform us about the ways to build our models of nature and the cosmos. But here we are on spaceship Earth. We're kind of trapped unless we send up a satellite. Even our Voyager probes are only about 0.001% of the way, something like that, to the nearest star, even though they've been traveling since the 70s, and they're the fastest things ever built by human beings. So the stars are very far away, but in our imagination we can get there. So in the Cosmos TV series, Neil deGrasse Tyson and Carl Sagan have had the spaceship of the imagination. I can't rip that off directly, but I will say that this is the spaceship of our daydreams. So we can imagine what it would be like to be on a spaceship traveling through the cosmos, witnessing the birth of stars and the result of the explosions of stars. And maybe it's also a time machine. I mean, why not? We're building it in our imagination. So maybe we can use it to go back and look at the way that the solar system was formed. So here we go. We're taking off in our spaceship of daydreams, and we're looking at a star that's about to go supernova. And then when the star goes supernova, it emits this giant, ever-expanding cloud of debris that fills space. This is kind of the way the Crab Nebula looks. You saw that those tendrils of matter coming out. of an exploding star. That's kind of how the Crab Nebula looks in the constellation Taurus. And imagine being in a spaceship witnessing such a thing. Of course, you'd have to have appropriate shielding and insurance policies and whatnot. And then from there, we can see that after sufficient supernovae, plural supernovas or supernovae, and you can see that it forms these giant conglomerates of gas and dust, and within these, like little diamond crystals, you see brand new stars coming into being in these tight clusters. There's a limit to how big a particular star can be, because as a star accumulates more and more material, it heats up more and more. Well, heat generates pressure. Remember that from junior high or freshman science in high school. Heat is associated with pressure, so as a star grows bigger and hotter and bigger and hotter, then that pressure tends to counteract the force of gravity, and it keeps the star from growing bigger. So there's a limit to how big stars can get. But in general, a given mass of gas and dust will collapse to form 50 to a few thousand stars. And in our spaceship daydream, we can get close and see how those things look. This, for many years, this is the Pleiades. For many years, astrophysicists thought that the Pleiades, these brilliant blue baby stars, were enshrouded in the gas that had collapsed to initially form them. And now the current thinking is these young stars just happen to be moving through an area that already had dust in it. But either way, you see that space, especially the space in our galaxy, there are some galaxies that lack gas and dust, but most of them, like our galaxy, have a lot of gas and dust still in it, and this is the raw stuff to make brand new stars. So you can make stars from gas and dust, and I talk about the fact that it's gas and dust. Really? There's dust that comes off of stars? I mean, they're really hot. If I tried to sprinkle dust into the sun, it would be vaporized and turn into atoms and ions. So how can stars make dust, right? Well, when stars, whether they explode in supernovas or whether they just puff out into a nova, like a planetary nebula, some of the lower mass stars like our sun will just sort of get hotter. They'll start burning helium in their cores, and they'll make carbon and nitrogen and oxygen. So even our star makes some of those elements. And as it heats up and burns these heavier elements, it heats and it puffs up, and it'll just emit this constant stream of minerals. Carbon and not our star, but heavier stars will emit silicon and whatnot. Well, what's one of the things you can do with carbon, right? If you've got a star that has a lot of carbon in it, and it's hot near the star, astrophysicists and mineralogists speculate that the first mineral, a mineral must be crystalline, and it must be made by a natural process. That's a couple of the things of a definition of a mineral. They speculate that the very first mineral made in the universe was diamond, proximal to some of these hot stars that were bleeding off material that they had previously synthesized from hydrogen and helium. So little tiny grains of diamond, much smaller than a pinhead, got embedded as part of this dust. And silicon. Stars make copious amounts of silicon. And what did I say about our star? It makes carbon and nitrogen and oxygen. Well, oxygen and silicon together make quartz, right? So a lot of the things, the raw atoms that come off of stars as they're shedding some of their mass as a prelude to collapsing and dying, some of the raw material that boils off of the surface of stars is dust. Grains of quartz and diamond, graphite, another way that carbon atoms can arrange itself at a cooler temperature. So you get a lot of the raw material of rocks, strangely, directly from stars. So when you look around at the Earth and you say, how did this granitic crust come about from the forges of stars, there is a scientific explanation about how you can get from stars that create these heavy elements directly to making rocks and dust and whatnot. You know, stars are hot, but space is mostly empty and cold. So you take this same material that started off blisteringly hot as atomic fragments in a star, and you throw them into the cold, dark recesses of space, and if there's enough of them nearby each other, they'll form chemical bonds, just like stuff on Earth makes chemical bonds. So, sometimes when a star forms, in fact, probably it's incorrect to say sometimes, it's probably more accurate to say darn near every time a new star forms, it will be surrounded by a disk of gas and dust. Now, why is it a disk? Why isn't it a sphere, right? If it's all collapsing towards a central point, then why does it make a ring? Why does Saturn make rings around Saturn? Why is it a ring instead of a sphere? Well, it's similar to the reason why if you spin around with your hands over your head and you do it fast enough, which I can't do because I'm old and not very agile, and I fall over, but if you spin around fast enough with your arms like a figure skater, ice skater, you'll feel a force on your arms. And the force will try to pull your arms to the side, directly to your side. Well, that same thing happens to any gas and dust that's spinning around a central point. As long as it has some angular momentum to begin with, it will collide with other particles, it will bleed off some of its tangential angular momentum, and will end up with just radial angular momentum. So even if you start with a collapsing cloud of gas and dust, through collisions of these particles with each other, as they exchange the direction of their angular momentum, it'll turn into a disk of gas and dust. Does that make sense to everybody? Okay. So you get these disks.
Could you spin a couple more times?
No. My
be...
union contract, there's a limit. So you get these disks of gas and dust, and within the disks you can get little eddies and vortices. Well, some of those eddies and vortices also collect gas and dust, including the same gas that makes up the new star, hydrogen and helium. All right, so you get these little vortices, and they're like, oh, I want to be a star too, but they just can't. They don't have enough material. So you get failed stars. You get things like Jupiter, right? Jupiter is made out of essentially the same stuff as the sun, is there's just not enough of it to collapse down and make high pressure, high temperature cores to generate nuclear fusion. However, in many cases, you will have multiple stars generated from the same collapsing cloud of dust and gas. In fact, most of the stars in the universe are in multiple star systems. You've got double stars and triple stars and quadruple stars and systems of 20 stars, and it just gets arbitrarily complicated because nature doesn't care whether we can solve the equation or not. It just does what it does. We can't, by the way, after hundreds of years of trying, the highest number of gravitationally bound objects that we can predict its trajectory perfectly for which we can, forget my grammar. Anyway, the largest number of objects that we can calculate the future of with arbitrary precision is 2. Not 20, not 3. That's why you hear something called the 3-body problem. Once you add a third object to a mutually gravitating set, well, then you have to simulate it with a computer. And you can't write out an analytic equation that tells you the arbitrary future progress of that system. Fortunately, for systems like our own solar system, if several of the bodies have a trivial amount of mass compared to the gravitating central mass, then you can mostly, in most cases, for most contexts, ignore the gravitational tug of everything else except the central star. And from an astrophysical standpoint, our solar system has two objects. You know what they are? The sun and Jupiter. So if you're an astrophysicist and you want to know how the solar system evolves over time, as long as you take into account the gravitational tugs of the sun and Jupiter, you're going to be pretty safe. Anybody have a guess? There's probably some of you who know, who've read about this or whatever, but anybody want to take a guess? I'm not going to laugh at you if you're wrong. How many of you might chuckle? Anybody have a guess on how much of the mass of the solar system is in the sun versus how much is in Jupiter? Any guesses?
99.9.
99.9. You've been reading.
No, I haven't.
No, okay, then that's good. It's 99.98% of the mass of the solar system is in the combination of the sun, and that's it. 99.98% of the mass of the solar system is in the sun. And 0.02% essentially of the mass of the solar system is in Jupiter. So the sun is really big. And you get these tiny little vortices and eddies, and they form just tiny little bits of fluffy matter, right? They got lots of hydrogen, and they got, sulfur and nitrogen and helium and whatnot. But some of those little fluffy bits, they form, because of the way gravity works, you get stable orbits and unstable orbits and mutual interaction and whatnot. For the similar reason that you see gaps in the rings of Saturn, you also see gaps in what are called protoplanetary disks. So this picture shows real protoplanetary disks that have been discovered out in our galaxy. There are others in other galaxies, but they're too small to see. So this uses radio telescopes, radio waves, because radio waves can see the hot dust and gas. And it's hot enough to emit infrared and radio signals, but it's not hot enough to emit visible light. But anyway, look at, this is real pictures of solar systems being born today. And you can see the gaps in the rings. And you can see the hot central bulge where the new star is forming. And there are lots of these. Some of them oriented a little bit out of the plane of our vision, so they look oblate a little bit. But these are real pictures of real solar systems being generated today. And imagine being in our imaginary ship Daydream and coming up on one of these things, and you see it dynamically swirling. You see the gas and the dust swirling in it. And you see these little nodules within the swirling rings encircling the central star. And these are the nuggets that form new planets. And there's all kinds of complicated science about this. There's a thing called the ice ring. You get far enough away from the central star and things cool down. And if it cools down enough, instead of having liquid water, you get ice water. Well, there are different physical properties of ice water versus liquid water, and there are different isotopes of elements in nature. There's heavy water, you've heard of that. There's heavy water, there's regular light water, there's heavy hydrogen, there's heavy oxygen, there's O16, which is normal oxygen, there's a smattering of O18, which has a couple more neutrons. Anyway, as something gets heavier, it responds differently to the thermal pressures around it. When something bumps into you, if you're heavier, you're not going to move as far. If you're a lightweight, something bumps into you, you're going to go shooting across the room, right? Well, the same thing happens for atoms. So heavier atoms tend to stay put and whatnot. So using isotopic analysis, the same chemical element, hydrogen or oxygen, you can tell where and what the physical conditions were like, where a particular molecule or atom precipitated into some material stuff in a meteorite or in a comet and whatnot. And there's in these protoplanetary disks, there's this ice line where it's too hot to be close to the sun without being either vapor or water. And then beyond that, you get a lot of ice accumulating. So there's this complicated physical chemistry that happens in the environs of a new star, and it's formulating and it's coalescing planets. Another thing that happens is that some of these volatile molecules, molecules that tend to make gases rather than solids, so things like CO2 and NO, nitrous oxide and whatnot, some of these that form gases, if they are accumulating around a planet that is forming in a pre-solar nebula or in a protoplanetary disk, then if they're too close to the central heat of the star at the center of that solar system, the heat will cause some of these lightweight atoms around forming planets to literally boil off into space, to be blown further away where it's cooler. And that's one of the reasons that the so-called terrestrial planets in our solar system, Mercury, Venus, Earth, and Mars, don't have thick envelopes of hydrogen and helium, even though most of the stuff in the universe is hydrogen and helium by a long shot, and most of the stuff in the outer planets is hydrogen and helium. It's because it's too hot for those very lightweight gases. What happens when you let go of a helium balloon or a hydrogen zeppelin? They float. They go up in the atmosphere, right? Those gases go up because actually the heavier atoms fall down below them and the lighter stuff percolates up. And it percolates up to the top of the atmosphere where it's hot enough for the heat of the sun just to strip away all of that stuff from the inner planets. So what are you left with? It's a good question. Part 2, the formation of the Earth. I think I'm going to get through my 40 slides. This is great. Formation of the Earth. In our Daydream spaceship, we're hovering over baby Earth, and it looks a lot like this, up to a couple 100 million years, or a little less than 100 million years after it coalesced from all the planetismals, a bunch of asteroids. Nomenclature becomes a bit difficult in many times in science. You're trying to draw a firm dividing line between a planet and a planetesimal and a planetoid and a dwarf planet and we get all these names and it helps us talk about these things, but nature doesn't care. It's just, oh look, there's a bit of matter. Big piece of matter, little piece of matter, nature knows what to do with it, right? But we want to put categories on it. But one of the categories they've come up with is planetismals, which were asteroids that existed at the time of the formation of the solar system. And these asteroids smushed together, technically smushed, they smushed together and agglomerated into ever bigger bundles of matter. And those became planets. So that's why they're called planetismals instead of asteroids. They're the same thing. Anyway, shortly, within a million years or so, a couple million years after the large coalescing happened in our protoplanetary disk, the Earth looked something like this. It was hot, it was an amorphous blob of stuff, we'll talk about the stuff in a minute, and it was full of magma. And, here we go in our daydream, and we see these planetismals smashing into the baby Earth, and it's all heated up, and just magma maelstrom. So it's a good thing we have shields on our ship. And here's another depiction of how the baby Earth might have looked. The sun was actually cooler earlier in its history, and there's all kinds of current research and controversy about, how hot was it when the Earth formed, how hot was it because of sunlight, and then the primitive atmosphere of the Earth would have been rich in methane, and methane, if you've ever seen a picture of what's the moon that has the thick methane atmosphere? Triton, yeah. It's like orangish atmosphere. So if you get enough methane, it's this thick smog, and it makes trapping sunlight. It's a fantastic greenhouse gas, as you've learned in other contexts. So a methane-rich atmosphere was very plausible for the early Earth, and so it trapped a lot of heat, a lot of greenhouse heat. So maybe the Earth was a lot hotter than it would be for the same irradiation level today. And in any case, along comes this, oh my gosh, what was that? Okay, well, that's important. That's Thea, the name of, was it an alternative name for the moon goddess, something like that? I could have that wrong, I'm just, this is off the top of my head. But anyway, somewhere within a few million years of the Earth forming, I got a big thwack by another thing that was on its way towards being a planet. It was about the size of Mars. And the material from these two protoplanets merged. And the lighter stuff, the lighter weight stuff of lower specific gravity, was splooshed off and condensed to form material that became the moon. And the moon, through and through, is essentially the same kind of material that the Earth's crust is. Right? So it couldn't have formed as an agglomerating body with iron and nickel and some of the other heavier things that we find on Earth. Instead, the iron and nickel that were in that Mars-sized thing sunk into the core of our Earth, and the outer crust of both congealed into this, like you drop a water droplet into a pond and you see a ball shoot up, right? You've seen a slow motion film of a drop of water. Well, that was probably a good thing, because a lot of what would otherwise be a very, very thick crust of material on the Earth, or at least thicker, a lot of that got sloughed off to form the moon. So it thinned Earth's crust. That's one good thing. Another thing it did was it smushed into the Earth and knocked it akimbo. And so the Earth, instead of orbiting in the plane of the protoplanetary disk with its rotation axis aligned perpendicular to the revolution of the disk, it was knocked about 23 degrees to its side. And that's why we have seasons, right? And then my other favorite story, plausible story about the moon, is the moon, because it's relatively close to Earth, incites tides. Right, instigates tides on the Earth. And some people speculate that some of the processes vital to the formation of life happen in tide pools. Well, no moon, no tide pools. Right? So the moon has been very, very important in the history of the Earth. If you want to spend a fun afternoon sometime, one of the things I like to do, and I've not finished yet because I get distracted by something shiny. One of the things that would be fun for an afternoon is to sit down and imagine what life would be like on a planet with no seasons, right? Life on Earth has evolved all sorts of adaptations, migratory patterns, climatic patterns, climatic patterns. So it's climate, it's life, the distribution of life over its surface, deciduous trees that lose their leaves, and changing of the seasons. So many adaptations on Earth are a direct consequence of the Earth having seasons. What would it be like? There's your afternoon activity. And it's fun to do this in groups at least of two, because you can feed ideas back and forth. Imagine what it would be like to be on a planet that evolved life, but which didn't have seasons. What would life be like? No need for trees to lose their leaves. No need for migratory seasonal migrations of lots of animals and fish and whatnot. What would it be like? How would the weather be different? Right? The tilt of the Earth causes the ice caps to wax and wane over time, with the summer heating and the winter cooling. Just think about that. Think about all the things that are entailed in the fact that our planet has got a tilt of 23 degrees, and what it would be like to be on a planet without that. And then go write your science fiction story, and we'll compare them next year. And this is what the moon looks like today. This is an actual photograph of the Earth and moon taken by a NASA probe satellite of some sort. All right. Remember this idea of the supernova that's blasting all of those yummy, crunchy elements out into space. You've got iron and silicon and oxygen and neon and so on and so on. I don't know that those are elements, but they ought to be. Well, about 4.6 billion years ago, there came a supernova in a region thick with gas and dust. And this supernova caused a shock wave that coursed through this interstellar material. And as the shock wave made its way from hither to yon, it caused disturbances in the material in this gas and dust cloud, and those disturbances initiated the formation of brand new stars. So a supernova doesn't just litter the nearby space with heavy elements, it actually produces an energetic shock wave that causes other gas and dust to sort of wake up and say, hey, you know what, we can do that. Give us a few billion years, but we can do that. And so a supernova not just populates and fertilizes interstellar space with a salting of heavy elements, but it also literally instigates the formation of new solar systems. And somewhere between 5 and 4.6 billion years ago, there was a supernova that instigated the formation of a new solar system that we call the solar system. Yeah, we're good at words. So our solar system benefited from having the detritus of at least one prior supernova. Now, how many of you saw the news story from a month ago about some pre-solar grains that were found in a meteorite? And these pre-solar grains using beryllium and some other isotopic analysis, which I could explain in some detail, but for the sake of time, I'm going to pass through it. If you have a question later, you can ask me. But using isotopic analysis, they can sort of use atomic clocks that are locked into minerals at the juncture, at the point in time in which these minerals condense to form a solid. They lock these atoms inside of them. And then over the course of millions or billions or thousands, if you're doing carbon dating, over the course of time, these locked elements, locked in place, go through atomic fission, decay. And you can measure the ratio, I guess I am talking about it. You can measure the ratio of the daughter particles to the original cryogenitor particles, and knowing the half-lives of these elements, which we measure in laboratories all the time, you can use this ratio, rationization, to look at the isotopes and figure out how long that material has been in situ. So you can look at volcanic rocks, you can look at rocks that are meteorites, and you can determine how long some of the isotopes that is within them have been in situ. And they took a piece of a meteorite that crashed to Earth in 1969, one of the most famous meteorites to ever hit Earth, because it left behind some really yummy debris. And it's called the Murchison meteorite, because it landed outside of Murchison, Australia. Right? How was that? And they have looked at the microscopic structure of some of the little crystal grains within this meteorite. And just last month, they said that they found within this meteorite the oldest material that has ever been found on planet Earth. It's so old, it's older than the planet Earth. These little grains of crystal inside this meteorite are 7 billion years old, half as old as the universe itself. And these grains were formed from the dust as the material cooled off from an ancient supernova. So at some point, this meteorite, or the stuff that's in it, was coalescing in a region of space that was being fertilized by a supernova, probably more than one. Because our Earth started forming about 4.6 billion years ago due to a shock wave from a relatively recent, I don't know how you can get away with calling that recent, supernova. Well, there were supernovae before that. So we're in a region of gas and dust that was enriched by all these heavy elements. And not just our sun formed, but other suns as well. In fact, I don't have it written down here, and it's got a cryptic name like HD 5732. I'm making up that number part, but it is HD something. There's a star that astronomers have identified out in the wider cosmos, not too far away from us, just a few hundred light years, that almost perfectly matches the chemical signature and the age of our sun. So they think that, remember, this shock wave didn't just cause one protoplanetary disk, it caused many. So the sister star to our sun has been found. And there's probably many others that haven't been discovered or noted yet. But how does all of this material, how does it turn into Earth? Well, now it's time for some science, and you can't do science without a graph. So this shows the cosmic abundances of elements in the universe, and it's a logarithmic scale. So if your peak is a little bit higher than other peaks, well then you're quite a bit more abundant. And as you see from this graph, hydrogen and helium are by far the most predominant and prominent elements in the universe. And then it takes a sad turn. Lithium, beryllium, and boron are sort of the also-rans in the cosmological element menagerie. That's because lithium, beryllium, and boron are not formed in stars. Remember last time I was talking about the metabolism of stars and the alchemy of stars, and I said that there was this wall. And this wall prevented nucleosynthesis from synthesizing elements beyond helium. And it's a darn good, well, not a good thing, but it's an interesting thing, because if that wall of energy wasn't there, the energy that makes it less likely that these lighter elements will be formed, if that wall weren't there, then the Big Bang would have synthesized all of the elements of nature. It would have been hot enough and dense enough. But you know, you can't get to lithium, you can't get to beryllium, and you can't get beyond boron. And so the Big Bang, when it was hot enough to do its magic, I don't want to call it magic because it's physics. When it was hot enough to do its physics, it just couldn't make the heavier elements. So we ended up with hydrogen, helium, and just a smattering of lithium. But once stars got going, population 3 stars got going in the universe, you get many of these other peaks, including carbon. What is the third highest, quiz time, what is the third highest peak on this graph?
Oxygen.
How about that? The third most common element in the universe is oxygen. How about that? So here's the rank of the elements in cosmological distribution. And then we can see the solar system abundances in this orange chart. And there's a little bit of discrepancy. This discrepancy has to do with the physical chemistry of the pre-solar nebula, right? How hot it was, where these elements formed. Some were ejected because they were too lightweight to hang around and whatnot. So there's a little shifting here and there, but it's all pretty explainable by astrophysicists. Nothing magical, in fact. And once again, it's still in both lists. Number 3 is oxygen. How about that? You look at Earth. What's the composition of Earth? It's It's got its mantle, it's got its lithosphere, it's got its core. A lot of the heavier elements sank to the core and whatnot. But mostly it's made of rock. Not very surprising, I suspect. Most of the Earth is made of rock. And here's some of the rock. So, about half of the volume of the planet Earth, if you think about all the atoms and how they pack together, about half of the volume of Earth comes from oxygen. So, looking at it volumetrically, Earth is about 50% oxygen. And yet it's made of rock. I mean, isn't oxygen a gas that we breathe? How does that happen? Look at all of these compounds. This is chemical composition of granite. These are the different ways granite can be formed. All these tag-along materials are attached to oxygen. This is how the Earth can be 50% oxygen. Solid. Next time, I'll tell you what, next time you stub your toe on a rock, don't worry about it, it's mostly oxygen. All right? So, you know, the baby Earth was hot, and it had these fractures in it, and magma. It was just, to borrow a metaphor from most of our religious heritages, collective religious heritage, it was a hellish place. I guess hell is Greek, isn't it? Or is it Roman? The Christians borrowed the idea, like they borrowed a lot from the Babylonians and the Egyptians and whatnot. All right, so we've got this Earth with its various abundances. Notice that the abundances on Earth, well, what happened to the hydrogen and the carbon? I said hydrogen and carbon were pretty common too. Well, carbon and hydrogen latch on to other atoms and they make lightweight gases. And lightweight gases in the relatively puny gravity of the Earth, watch. My little muscles can overcome the gravity of Earth. That's how puny the Earth is, right? So in the puny gravity of the Earth, some of the lightweight volatile gases made from carbon and hydrogen and whatnot bled off, including a lot of the oxygen gas. But oxygen isn't just a gas. You see oxygen, silicon, aluminum, iron, calcium, magnesium. This is what rocks are made out of. Rocks aren't made out of an element called rock. Rocks are made out of elements called oxygen and iron and aluminum. And this is the sizes of some of the atoms. Atomic size versus, these are the sizes of various ions. And to begin with, oxygen is relatively small. It's on the first line, third from the right. And oxygen is a relatively small atom, but when you combine oxygen in either an ionic or a covalent bond, the effective size of oxygen gets much bigger. So here's the way silicon tetrahedron looks, SiO4, quartz. One of the most common pieces of rock chemistry on Earth. The silicon is safely nestled in a pyramid of oxygen atoms. And the oxygen atoms, once they enter into this ionic bond with silicon, the oxygen atoms puff up to much larger physically than they would have been if they were neutral oxygen atoms. And this is one of the reasons that the Earth is largely oxygen. And by largely, I mean its physical size. Right? And then you get all of these complicated processes where you get weathering and whatnot. But in order for that to happen, you must get crust. So we're going to talk about the ages of the Earth. And I'm going to blast through this in a few minutes because I can get to the most interesting stuff. So the original Earth was called Black Earth. And it was essentially basalt, basaltic crust. Basalt is another way to use oxygen to make rock. Right? And this was called the Hadean era, the hellish era on Earth. And it lasted until about 100 million years after the initial formation of the Earth. First came olivine, a greenish magnesium silicate, which sank in Earth's magma surface. Remember olivine. Next month, I'm going to talk about olivine. It's going to have a star role when I talk about abiogenesis, the formation of non-living things from geology and geochemistry. Remember olivine. And then as it cooled a little bit, you got feldspar, a calcium aluminum silicate. The rock stayed on the surface of the Earth. It didn't sink as deeply like olivine did. Feldspar hung around on the moon. There are whole mountains of feldspar on the moon. And these are just complicated names for oxygen-rich minerals. Most of them are silicates. So you get all of these complicated things happening. And about the same time that you will have the right temperature and conditions for these things to form, you also form the most precious stone known to science. You remember, I don't know, when I was a kid, I used to see these advertisements on TV about genuine cubic zirconium. You know, this fake diamond is almost indistinguishable from real diamond. You want it because it's cheap. Zirconium and zircon crystals are far, far more valuable to science than are diamonds. Because zircons are tough little buggers. You get a zircon crystal and it can last for billions of years. It can be weathered by glaciers, it can be blasted by sandstorms, it can go through great pressures and temperatures coming in and out of volcanoes, and it's still a crystal of zircon. Really, really durable stuff. And zircon has a particular affection, there I go anthropomorphizing nature, which I shouldn't do because I can't even pronounce it. And zircon loves uranium. And so zircon grabs uranium, but zircon hates lead. Oh, very good. Well, what does uranium turn into if left alone long enough? Lead. So zircon initially gobbles up uranium. The uranium gets bored of sitting around after a while and says, no, I'm going to be lead instead. And now the zircon, even though it never wanted it, ends up with lead inside of it, and a little bit of uranium. Well, doing this fractional isotopic analysis again, you can use zircon crystals as phenomenal timekeepers for geologic strata and geologic processes. So some of the oldest material on Earth has been dated using isotopes trapped in zircon crystals. So from about 100 million years to 200 million years, the Earth is water. Most of the water came from inside the Earth. Remember these planetismals, these asteroids that made the Earth? Right? It used to be thought back in the 70s and 80s that comets blasted onto the Earth and brought water. Now the current thinking, might change, but the current thinking is that it's actually the protoplanetesimal planetoid asteroid things that carried along with them water, and it got incorporated into the mass of the Earth. And then as the Earth heated up, it spewed forth steam, explosive volcanic eruptions. And a lot of times when you see an explosive volcano, it's because of steam. Mount St. Helens, largely because of steam, water trapped in the rocks. So after over 100 million years or so, the Earth stopped being churned as much by space missiles. Various volatile gases like H2S, hydrogen sulfide, NH3, CH4, ammonia, water, sulfur dioxide, etc. A lot of these gases escaped the Earth, escaped the material of the Earth, and populated the atmosphere, that it was not a place you wanted to breathe. And then, about 200 million years to about 1 billion years ago, Earth cooled enough that the lighter, fluffier bits of Earth floated to the top. And these little fluffy bits are called granite. All right? So granite is the fluffiest bit of the Earth. All right? That's why the crusts, Earth's crusts, are made from granite. Right? It's the lightweight stuff that comes to the top, and it made these volcanic island chains, and these island chains smushed together and made continents. And over time, the continents have moved and accumulated and whatnot. You've seen pictures like this. I'm not going to go through this in detail, but continents move, driven by the churning heat of the earth. And then life comes along. We're not going to talk about that. We'll talk about that next time. And then you get red Earth. Soon after life was invented by the universe, life said, iron, yum, 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 yum. Oxygen, oh, I love oxygen, right? Well, before life loved oxygen, life hated oxygen. It's kind of had a love-hate relationship with oxygen. And one of the things that happened on the early Earth is that iron ions were dissolved in seawater, and then life comes along and makes a lot of oxygen. As a byproduct, plant life makes oxygen. And now the oxygen is dissolved in seawater. What happens when you get oxygen and iron dissolved together?
Rust.
They make rust. The most valuable iron mines on Earth are mining these red, rusty layers called banded iron deposits that were laid down about 1 billion years ago. During Science Sunday, just real quickly, during Sidewalk Science last year, Joanne and I talked to a guy who used to work in a mine up in northern Minnesota, and he said, I worked in this mine, and I wish I'd have known to look for fossils. I said, were you mining iron in Minnesota? He said, yes. I said, you were mining fossils. All right, and then there came white Earth, right? Because of outgassing and periods of cooling and heating in the Earth, there's all kinds of geologic and geochemical evidence that it's at least 3 times in history the Earth has been nearly covered, if not completely covered, probably just nearly covered, because there's evidence that there was a thin band of at least slush around the equator because life didn't die. And then, finally, after a few billion years, let's open our spaceship door and go outside because it's a beautiful green Earth. And we'll talk more about formation of life next time. I got through my slides. All right, you have to go to church. Well, you have to go to church. Those of you who are willing to be a few minutes late or don't want to go to church, you can stay and ask questions.
I have a question.
Mm-hmm.
When you were showing those rings of material around forming stars that will eventually form planets, it seems to me you need a guy with a catcher's mitt to catch that stuff so it all comes together to make a planet. So how do you get from that ring of material? How do you get from that ring of material?
So how do you get from a ring of evenly distributed dust and gas to a center of nucleation? That was your question.
Right.
Right. Just random chance, right? I mean, if I've got random bits of momentum, and it did start off as a sphere, and you're colliding together, well, there'll just random chance there will be a little area that is denser than the surrounding areas, and like a growing snowball, that will get a little more things will collide with a big thing than new things collide with a small thing. So big things get bigger, up to a limit. Again, we've got the heat pressure from the sun and other things colliding, breaking them apart. So on balance, you get some areas that are able to accumulate mass, and it's just gravity and electrostatics. Other questions?
Why are the center masses spinning in the first place?
Why are the center masses spinning? Because everything in the universe, generally speaking, is moving, and you can transfer or transform linear momentum into angular momentum through collisions. So if you've got all this stuff that's moving and it goes, well, hey, I like you, you've got gravity, right? Then it bends and comes together. Well, if you get a bending straight line, that's a curve. And if you get enough of that curviness going on, then it becomes a circle, right? So through the transfer or transformation of linear momentum into angular momentum, momentum is still conserved. Movement is still movement. But instead of being movement in a straight line, it becomes movement in a circle. And as far as astronomers have discovered, everything in the universe, every object, from a galaxy to a planet to a star, spins.
Could you anticipate any linearity across the whole universe, that the universe has some linear aspect to it, or, I mean, we see things in all sorts of different presentations, but you'd think that from an explosion that there might be some linear element.
But it wasn't an explosion.
Yeah, well,
Right.
everything, remember the surface of a balloon, the Big Bang, you stick pennies on the surface of a balloon and then blow it up. The pennies don't get bigger, but the balloon gets bigger, and each penny is getting further away from every other penny. That's a good analogy for the expansion of space. Is that linear? Well, in some sense. There are some speculations that the universe as a whole is rotating, but how would you know? Right? So, at the very least, things are in motion because gravity pulls things together. If you've got a weak gravitating thing and a strong gravitating thing, and I'm in the middle, I'm going to move towards a strong gravitating thing. So everything seems to be in motion, and that linear motion can get translated into rotational motion. I don't know if that answered your question or not. Hey,
There's also the suggestion that simply because the galaxy is spinning, that when a star is formed, it takes up some of that momentum.
Yeah.
And so begins to
Right.
form in that and begins to spin in the direction that it will go, it will roll in.
right, so galaxies are eddies in a gigantic clump of gas left over from the Big Bang. They're just spinning vortices. Remember, most galaxies are also kind of pancake-shaped. Many galaxies. And so the same thing that causes planets to form in the eddying disk of a pre-solar nebula caused stars to form in the eddying vortices in the overall spinning mass of gas that turned into the galaxy. It's the same physics operating at different scales. Yes?
I was curious, it seems kind of counterintuitive that there's a white phase to the Earth when things were so hot back then. Was it like a refrigeration effect? Something was evaporating and making it cooler or something?
That's a great suggestion, evaporative cooling. So it has to do with feedback, very complicated feedback mechanisms of getting a lot of ammonia and other things in the atmosphere that block sunlight. Well, if you block sunlight or reflect sunlight back into space before it reaches the surface of the Earth, the water that's on the surface of the Earth can freeze. So even though it might have been warm in the environment, in the solar system environs of the Earth insulated itself from sunlight. Formation of water clouds. It rained all the time on baby Earth. I mean, there was never a clear sunny day. It was always raining. These volcanoes were everywhere, emitting huge, copious geysers of steam and water that turned into clouds, so that clouds are white, they reflect light. Right? So there's this balance between reflecting light and trapping light. There was also implicated in the freezing of Earth is the continental drift. When the first continent, I forget its name, I've got it written down in here, I forget its name. Huh? Pangaea came long afterwards. It was a supercontinent that was long after this initial.
Not
Anyway,
Gondwana land or anything. Right?
this is earlier still.
Okay.
No traces of it left. But anyway, this continent originally was near the equator. Well, the land tends to reflect more light back than ocean. So if you have a lot of reflective land near the equator, where the Earth gets much of its heat and light is on the equator, and this light is being reflected back, it causes the Earth to cool. So all of these complicated feedback mechanisms of reflectivity and heat trapping and whatnot combined to, and this is a post hoc explanation, right? Geophysicists didn't say, you know, with this continent there, I bet the Earth froze, right? Instead, they said, holy crap, the Earth froze. And then they went looking for evidence and plausible explanations about why that happened. And there's all these complex feedback things, right? All right, we gotta go, but I'll be around and I'll be back in a moment.